Welcome to Homework Lib.
Over here we want to calculate the pH up to 2 decimal places of a solution that is at equilibrium of barium fluoride, which has a KPS or KSP constant equal to 1.7 times 10 to the minus 6. And we're also given as information that the value for Ka for HF is going to be equal to 6.8 times 10 to the minus 4. So if we know that the solution is at equilibrium, that means that we have a saturated solution. So the concentrations are going to be given by the solubility product constant. In this case, what we're going to have is that the concentration of the ions that we're going to have in solution, which are barium 2 plus 2 of F minus, are going to be given by the following ice table. Initially, the amount of the solid at the equilibrium doesn't matter because we know that condensed phases do not enter into equilibrium equations, but a certain amount x is going to go into solution. So we're going to generate plus x plus 2x, giving at the equilibrium a quantity of x and 2x. Thus, the solubility product constant, that is going to be equal to the concentration of barium 2 plus times the concentration of F minus squared, will be equal to x times 2x squared, which gives us 4x cubed. Since we're given the value for KSP, we can calculate the value of x. That would be equal to KSP divided by 4 and taking the cubic root of that. The value for KSP in this case is going to be equal to 1.7 times 10 to the minus 6 divided by 4, and over here all to the 1/3. This is going to give us a value for x equal to 7.518 5 times 10 to the minus 3 molar. But the quantity that we're interested in is the concentration of F minus. And the concentration of F minus at equilibrium is going to be equal to 2 times x. So we need to multiply this value by 2, and we're going to get 0.015 037 molar. Now this quantity we can employ it by finding the value for the pH. The F minus ion is going to react in the presence of water, all of this in aqueous medium. This is going to be a liquid, in order to generate HF plus OH minus. We're going to have the following ice table. We're going to start with C0. This is going to be our initial concentration, equal to this value over here, the one that we found from the solubility product equilibrium. The amount of water doesn't matter, and initially we have 0 of each of them. The amount of change is going to be minus x, doesn't matter, plus x and plus x. So at equilibrium we're going to end up with C0 minus x, and x. Now, the equation over here corresponds to Kb, not to Ka. And Kb is going to be equal to concentration of HF times the concentration of OH minus divided by the concentration of F minus that we have. Remember that Kb and Ka are going to be related by the fact that, let me put it over here, that the product of both of them is going to be equal to Kw. So Kb is equal to Kw divided by Ka. Recall that the value for Kw is going to be always equal to 10 to the minus 14. So 10 to the minus 14 divided by Ka, which is 6.8 times 10 to the minus 4. We get that Kb is equal to, Kb is going to be 1.47 times 10 to the minus 11. This is times. So this is going to be a super small value. Replacing the equilibrium concentrations, what we get is going to be x squared divided by C0 minus x, and this is equal to Kb, which I said that was 1.47 times 10 to the minus 11. So over here we can make the approximation that since we know that Kb is going to be super, super small. That means that x is very small. Under those conditions, C0 minus x is going to be approximately equal to C0. So this is going to be true whenever x is lower or equal than 5% of C0. This is going to be a good approximation under those conditions. So solving for x, this is going to be equal to the square root of kb times C0. This is going to be a square root of 1.47 times 10 to the minus 11 multiplied by my initial concentration, which is the value that we got here, 0.015, 15037. X is going to be equal to 4.7025 times 10 to the minus 7 molar concentration. And guess what? This value for x is equal to the concentration of OH minus. We can get that result from our ice table over here. And finally, we can calculate POH is equal to minus logarithm of OH minus. And additionally to that, the pH is going to be equal to 14 minus POH. The result for both of them is going to be 6.33 and 7.67, respectively. In this case, the value that we required was the value for pH up to 2 decimal places, and this is going to be your final result.